Okay. Are these axioms enough for what we want to do? I mentioned a while ago that we want probabilities to be numbers between 0 and 1. Here's an axiom that tells you that probabilities are non-negative. Should we have another axiom that tells us that probabilities are less than or equal to 1? It's a desirable property. We would like to have it in our hands. Okay, why is it not in that list? Well, the people who are in the axiom-making business are mathematicians, and mathematicians tend to be pretty laconic. You don't say something if you don't have to say it. And this is the case here. We don't need that extra axiom because we can derive it from the existing axioms. Here's how it goes. 1 is the probability of the entire sample space. Here we're using the second axiom. Now, the sample space consists of A together with the complement of A. Okay, so this is, when I write the complement of A, I mean the complement of A inside the set omega. So we have omega, here's A, here's the complement of A, and the overall set is omega. Okay, now what's the next step? What should I do next? Which axiom should I use? We use axiom 3 because a set and the complement of that set are disjoint. They don't have any common elements. So axiom 3 applies and tells me that this is the probability of A plus the probability of A complement. In particular, the probability of A is equal to 1 minus the probability of A complement. And this is less than or equal to 1. Why? Because probabilities are non-negative by the first axiom. Okay, so we got the conclusion that we wanted. Probabilities are always less than or equal to 1, and this is a simple consequence of the 3 axioms that we have. This is a really nice argument because it actually uses each one of those axioms. The argument is simple, but you have to use all these 3 properties to get the conclusion that you want. Okay, so we can get interesting things out of our axioms. Can we get some more interesting ones? How about the union of 3 sets? What kind of probability should it have? So here's an event consisting of three pieces. And I want to say something about the probability of A union B union C. What I would like to say is that this probability is equal to the sum of the 3 individual probabilities. How can I do it? I have an axiom that tells me that I can do it for 2 events. I don't have an axiom for 3 events. Well, maybe I can massage things and still be able to use that axiom. And here's the trick. The union of 3 sets, you can think of it as forming the union of the first 2 sets and then taking the union with the 3rd set. Okay? So taking unions, you can take the unions in any order that you want. So here we have the union of 2 sets. Now, A, B, C are disjoint by assumption, or that's how I drew it. So if A, B, and C are disjoint, then A union B is disjoint from C. So here we have the union of 2 disjoint sets. So by the additivity axiom, the probability of that union is going to be the probability of the first set plus the probability of the second set. And now I can use the additivity axiom once more to write that this is probability of A plus probability of B plus probability of C. So by using this axiom, which was stated for 2 sets, we can actually derive a similar property for the union of 3 disjoint sets. And then you can repeat this argument as many times as you want. It's valid for the union of 10 disjoint sets, for the union of 100 disjoint sets, for the union of any finite number of sets. So if A1 up to In are disjoint, then the probability of A1 union AN is equal to the sum of the probabilities of the individual sets.